Well, hi, everybody. I'm here to step in and give you a quick little introduction to how differential equations show up in the real world. It turns out that differential equations are actually everywhere, and we see them in many different fields in many different places. And I just want to give you one example in this video of a place where differential equations do show up. Namely, I'm going to talk about a phenomenon called Newton's law of cooling. Now, just as a background, before I get into the details of this, I want to remind you that a differential equation, which I sometimes will abbreviate DE, is just an equation that involves one or more derivatives of an unknown function. So the goal is generally to solve for that unknown function. In this video, however, my primary purpose is simply going to be to show you an example of a differential equation. So I'm going to go up to my board. I want to imagine that I've got a hot cup of coffee right here. And I set it in the room at room temperature. And the coffee just sits there over time. Presumably, this hot cup of coffee is going to gradually cool down towards the temperature of the room. And that is, in fact, the spirit of what Newton's law of cooling says. Although Newton's law of cooling will tell us in a little more detail how that cooling occurs. I'm going to write down the statement of Newton's law of cooling in words first, and then I'll put a mathematical equation with it, a differential equation. Okay, so here's what it says. It says, in fact, let's just title this Newton's law of cooling. Newton's law of cooling says that the rate of change of the temperature of an object is proportional to the temperature difference. Okay, so the temperature difference, this is turning out to be the key thing. The temperature difference between the object and the surrounding medium. That's a little bit of a mouthful. Feel free to pause the video if you need more time to think about this or to write it down. But Newton's law of cooling is talking about the rate of change of something. And that means the derivative, right? We've learned in math that the derivative measures the rate of change. In this case, we're talking about the rate of change of the temperature of an object. So I'm going to set up a little bit of notation to help me describe that. I am going to let capital T of little t be the temperature of that object at time t. The temperature of the object at time t, capital T of little t. That's the temperature. This differential equation is talking about the rate of change of that temperature with respect to the variable, which is time. In other words, the differential equation is going to tell us something about this expression, right? The rate of change of the temperature as a function of time. That rate of change is proportional to the temperature difference between the object and the surrounding medium. So I'm actually going to make another notation, and I'm going to let T sub m be the temperature of the medium. The temperature of the medium, T sub m. for the purposes of this video, I'm going to assume that that temperature T sub m is a constant. The room temperature or the air temperature, whatever, is not changing. We'll assume that for simplicity right here. It's possible to extend the ideas of this video to handle situations where the medium has a temperature that's also changing. But for the purposes of this video, I'm going to assume that this temperature of the medium, T sub m, is a constant. And now I can come over here and fill in the rest of my differential equation. The rate of change of the temperature of the object is proportional to, I'm going to use a K for this. This is just what is called a proportionality constant. A proportionality constant. And it is proportional to the temperature difference between the object and the surrounding medium. So I do a subtraction right here between the temperature of the object and the surrounding medium. This, my friends, is my differential equation. It involves one or more derivatives, namely the first derivative of the unknown function. The unknown function is the temperature as a function of time. How hot is this coffee at any time t? Now, in a later video, I'm actually going to describe how we can solve this differential equation. However, for right now, I will suffice it to just give you a little sneak peek into what this temperature function looks like as a graph. Let's suppose we have a set of axes here. The time is going to go on the horizontal axis. The vertical axis will have the temperature on it. And let's assume that T sub m is just this constant temperature right here, and it doesn't change. If the initial temperature of my object is, let's say right here, I'm going to put that at time 0 on the y-axis. At least at this time, the difference between the temperature of the object and the temperature of the medium is pretty large. And so at this time value, what we can say is that this, this is a pretty large expression, so the rate of change would be pretty large, right? And in fact, it means that it's going to be a pretty steep slope at the beginning. But as the coffee or the object cools down, it gets closer to the temperature of the medium. And so the slope of this curve that I'm drawing gets less and less steep over time. If the coffee has been sitting here for a month, right, it's probably got a temperature that's very close to the temperature of the medium, and it's probably not changing much anymore, right? So that's the whole idea. Now, one thing that is a little strange here that you probably have noticed is that if this is a hot cup of coffee coming into a cooler room, this temperature difference is positive. Hot coffee into a colder room, you subtract, you're taking a bigger number minus a smaller number, that's positive. And yet you notice that the slope of this graph is negative. It actually would tell us that the proportionality constant would have to be negative to sort of make the two sides be equal to each other. If the derivative is negative, but the temperature difference is positive, then the K actually would need to be negative. So what people normally do, because that is true, that this proportionality constant is always negative, people will automatically, is everybody following this in your notes? Make sure you put a minus sign there. People will just go ahead and put that minus sign in there to begin with, because they already know that there needs to be a negative in this proportionality constant somewhere. And by putting that negative in there to begin with, they are actually allowing the constant K to be flipped back positive again. Okay, so this is actually the differential equation for Newton's law of cooling. In a future video, guys, I will explain how we actually solve this differential equation and solve for the temperature as a function of time. Ooh, that's hot. Guys, thanks for being here today. I appreciate you watching the video. If you have any questions, let me know. Keep in touch with me and take care. I look forward to seeing you all again soon. Bye for now.